I'm Jonathan Tomkin from the University of Illinois. So we have many different possible environmental policy approaches. How do we decide whether these policy approaches are worth implementing, that they're worth doing? Well, there's a number of approaches that policy experts use when assessing policy. And we're going to examine the major classes of those in this lecture. We're going to be looking at cost-benefit analysis, the precautionary principle, and risk management. In cost-benefit analysis, we compare the social benefits of a new piece of legislation with the social costs. So this is similar to when we did that net benefit calculation in the last lecture, but in this case, of course, we're considering the total society. So if the benefits outweigh the costs, then we can say a policy is worth doing. Cost-benefit analyses are usually done in currency, like in dollars here in the United States. So we try and get a dollar figure to the benefit of a piece of environmental legislation, and we compare that with the cost in dollars of enacting that legislation. You can immediately see there are some potential problems with this approach. Firstly, even if you concede that most things can be measured in dollars, and I think that's already a difficult stretch for a lot of situations, it can be difficult to get an accurate assessment of how much an environmental good is really worth in terms of dollars. Let's take an example. In the United States in 1983, there was a choice in environmental policy circles between lowering lead in petrol or removing lead altogether. Now, for a long time, cars ran on petrol that had a lead additive in it to help the engines run smoother. So this lead creates a benefit, right? It makes these engines more efficient. But lead also has a cost. By putting it in petrol, we're emitting it into the environment, and lead creates neurological impairment. So for any new policy then, the costs of removing lead from gasoline would be that we'd have to redesign our engines, we'd have to retool the refineries, so there would be some technological costs, and there would be a loss in the efficiency of how these cars were designed to run, at least in the short term. But the benefits would be is that we'd no longer have this lead pollutant going into the environment. And from a practical point of view, if you were to look at a good example of how lead is bad, is that lead is thought to reduce the intelligence of children. So how do we value that? Well, even if you accept, say, the IQ system, how much is an IQ point worth? And in fact, people doing a cost-benefit analysis actually included this in their calculations. They estimated the value of an IQ point to be between $1,000 and $8,000. In the end, a lot of these cost-benefit calculations weren't really used in the final legislation, which did ban lead in gasoline, which has widely been seen as a positive legislative step. But nevertheless, you can see, using cost-benefit analysis, although in principle goes straight to the heart of the equation that we looked at the start of this week's series of lectures, that is, we're looking at the total net social utility or welfare. In practice, it has many challenges, and if you look in the textbook, you'll see some of the ways that policymakers and environmental economists have tried to get over those challenges and make those estimates. Risk management is really a subset of cost-benefit analysis. In cost-benefit analysis, the cost is always clear. We have this given effect that is negative. In risk management, there might be a negative event that doesn't happen every time. There's just a chance of a negative event. So, for example, if you smoke, you know that there is a chance that smoking will cause a negative event, right? You might get cancer from it, you might get emphysema, and so on. But that's not for sure, that's not a given, that's not inevitable. So we have to make judgments in our own lives all the time when the dangers of a risk are outweighed by the benefits of taking that risk. Similarly, good policy needs to make those same calculations. In this case, we would say the benefit is worth doing if it's greater than the chance of risk multiplied by the magnitude of that risk. And again, like cost-benefit analysis, this can be difficult. Firstly, we have to have a good estimate of the cost of that risk. So if we go back to the example of a nuclear plant meltdown, how much damage will it do if there is a meltdown, right? That can be a difficult calculation to make. Then secondly, what's the odds of that happening? And especially for rare occurrences, that can be very hard. This is also difficult for people as we're not very good at statistics. And so some sorts of risks are much more salient in our minds than others. As an example, some people are terrified of flying because of the risk of crashing, whereas of course flying in a plane is seen as less risky than being driven in a car. Nevertheless, if we are examining a policy that will impact on the probabilities of some failure or some risk, we do need to use a risk management approach if we're to have even a chance of accounting for that risk correctly. Finally, as we saw in the genetically modified organisms lecture, another approach is to consider the precautionary principle. This is quite a popular approach in some places and is used in many pieces of legislation, for example, coming out of Europe. In the strong form, as we spoke about last time, the precautionary principle would require that if there's any level of risk at all, right, if scientists have not said this is completely safe, then we should not be allowed to go forward with whatever that situation is. In some ways, this is of course absurd. This would mean that you or I could never cross the street if we apply the precautionary principle, because after all, we might get hit by a bus. But in its weak form, you can be a little bit more forgiving, and you could use it when we don't know the level of risk. In some sense, we can calculate how risky it is to cross the street, but it's not so straightforward to figure out how would you even approach calculating how risky it is to release a new genetically modified organism into the environment. And as we saw with genetically modified organisms, there are potential problems with this tool. For example, it might mean that we fail to enact a policy or use a technology that would actually bring about a benefit, so we miss out on the chance to improve things. This brings us to another idea, which is how do we assess whether or not a policy has failed? Policies don't always work. Cane toads were introduced to Australia as a biological control on cane beetle populations. Cane beetles eat cane sugar and so were having a negative impact on local farmers. Cane toads didn't turn out to be a very good choice as a biological control. Not only did they fail to control the cane beetle, they're also a poisonous animal, and as they spread out throughout the large parts of Australia, they caused the deaths of large numbers of native animals that tried to eat them. We want to avoid environmental policies like this. Of course, sometimes the biggest failure is to do nothing. This is called a policy failure of omission. Before 1956, for example, thousands of Londoners died because there was no policy in place to prevent the build-up of toxic smog. That was a failure of policy. Another example, you might argue, is that an effort in the 1990s in the United States to increase federal fuel taxes in proportion to the carbon dioxide emitted failed. If we were to say this is a good policy because it's mitigating carbon dioxide emissions, why might it not have been passed by the legislative body, in this case Congress? We can think of many reasons. It could be susceptible to policy interference. If regulators are heavily influenced by lobbyists or an industry, the standard might not get through a political process. So clearly, just as we've always seen in this course, governments are just like people. Their judgments are not always correct, and not every law passed is a good one. I mentioned lobbyists or industry. There's actually a term for this. It's called mobilisation bias. It could exist in any type of political system. In a kingdom or a dictatorship, imagine that you're the brother or sister of the person who rules the country. Clearly, you'll have more of a voice in how that country gets run than the average person on the street. Similarly, in a democracy, we have lobbyists and people who are close to those who hold political positions, and these people can have more of a voice about what goes into legislation than the average person on the street does. In the United States, for example, lobbyists locate in DC, not in, say, downtown Kansas City. That's because they want to be close to the people who make the laws, make the policies that will affect their industries. This is called mobilisation bias, because some groups are more mobilised than others, and even if in a democratic system in principle one person equals one vote, groups that are more mobilised are more likely to see the legislation enacted in their favour. Industries subject to regulation have lots of incentive to modify the policy process. So, for example, to water down a polluter pays principle, or to remove mandates on how much pollution they're allowed to emit. They are concentrated interests, to use another political science term, and as they're concentrated, they can mobilise to stop or change legislation in a way that diffuse interests, that is perhaps the country as a whole, cannot. This uneven access can result in lopsided policy. On the other hand, environmental groups can form their own lobbying organisations and their own concentrated interests. And so sometimes there could be a balance between polluter groups and environmental groups. Again, however, the average citizen who is not one of these concentrated groups has a weaker role in the policy process. Political systems are run by people, and people are flawed. So even if we agree on an environmental goal, we might not come up with the best way to solve that problem, to meet that challenge. As individuals, we have our biases. It's actually very natural for us to look for evidence that supports our currently held positions, then makes us change those positions. And people in government and political parties in government are just the same. So although it's possible that governments might use science, be it natural science or social science, to support their views on a piece of legislation, they're not being unbiased in the way that they use that scientific evidence. An example might be biofuels. In some ways, it would be excellent if we're able to move away from fossil fuels that create carbon dioxide pollution and instead use a renewable biofuel energy resource. But as we've seen in previous lectures, the mandate in the United States that a certain amount of biofuel gets used in transport has had some significant negative effects. In the first place, it's not currently technologically feasible to produce enough biofuels to meet the mandates. Secondly, as we increase our biofuel production, we're also reducing the amount of farmland being used to produce other things. And many observers think that world food prices have been pushed up by this mandate. And this means that by requiring biofuels in American cars, we might be reducing the amount of food available in developing countries. Policy failures are very serious. Governments are just like individuals. They have limited amounts of time, resources, attention, money to address the problems. If we spend all of our efforts on inconsequential problems, we could miss our chance to move to a sustainable future because we ignored those problems that were truly important. Given finite resources, is there a framework in which we can try and figure out whether or not we're doing the right thing? Turns out that there is a way of trying to understand whether or not we're efficiently allocating our resources where they can do the most good. And we'll be looking at this in the next lecture.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.